So in this lecture, we're going to talk about underground cable and how we can model the impedances for underground cable. But before I get into the content, I know a lot of you in class in your introductions have talked about an interest in renewables. And so just for your background, what I would suggest is you maybe go to some of these sites here and learn a little bit more about the topic area. And I would say one of the better sites is the one for the National Renewable Energy Lab, or NREL. And this is just shows the address right here for the page. Basically, if you were going to go to this site, then you could actually see more information about their program. We have a number of our ex-students who are working there now. This is out in Colorado, and they also would hire interns as well. And so this is something I would really recommend you check out, because a lot of the premier programs in the United States in renewables are done through this NREL lab. Another source to consider would be for Department of Energy. There's a program referred to as SETO, Solar Energy Technologies Office. And so within the Department of Energy, what SETO does is it funds a lot of large projects in the United States that kind of push the envelope of solar technology. So it could get into panel design or inverters, or how to integrate systems into transmission distribution. At NC State, we've got several projects through the SETO office. And so if you want to know, what are kind of some of the major things going on in the US, maybe a little bit more on the vendor side, this would be another good resource. And then finally, if you want to see some good reports on integrating solar, I'd recommend you go to this site for the California Public Utilities Commission. California is one of the leaders in solar integration. And so they have a CPUC site. This is for the California Public Utility Commission. And then they have a sub-site here. It's actually not a sub-site, I guess. It's actually has a different website, but it's actually stuff that's funded by CPUC, where they actually then post all these different projects that's been funded related to solar integration. Some of these are older reports by now, but there's a lot of good reports they've done on solar integration, like especially into distribution systems. So this could also be another good resource. So I'm going to break the lecture into 3 parts, and I want to talk more about the physical characteristics of cables and how we actually would install these systems. And then in the second part, I'm going to get more into the impedance and admittance calculations. We didn't talk about admittance, which is the same as like capacitance, because for lines, there really isn't that much capacitance. There's a little bit, but not too much. But cables have a lot of capacitance associated with them. So when we talk about the modeling of cables, not only do we need to model the series impedance, the resistance and reactance, but we need to model the shunt capacitance to ground, where normally we break the capacitance in half. We put half on the left side, we put half on the right side. And this is going to have a major impact on voltage. And so anyway, I'm going to go through both the series impedance and the admittance or the capacitance calculations, and then just kind of work some examples through and show you how you can do some calculations for single phase and 3-phase. So if you haven't seen cables before, there's a lot of different combinations as far as construction. The one we're going to talk about most in this class is what we call jacketed concentric neutral. And so you have a phase conductor that's in the middle, and a lot of times this is stranded. You'll have an insulation, that's this white material. This is an insulation or dielectric. And then you'll have a neutral that consists of small strands of wire that are wrapped around the conductor shield, we call that. And so all these strands of wires put together give you kind of like your effective neutral return. You could have cable that's jacketed where it's covered on the outside. You can have cable that's not jacketed. You could have this put into a conduit, like a pipe. It could be a plastic pipe. It could be concrete. And then another sort of construction you see is what's referred to as a shielded cable, where instead of having separate wires, it's more of a solid type of a cover or uh, a shield. And so sometimes this is referred to as tape shield. Other sorts of cables that you would see would just maybe just be covered wire. This is an example here of what's called covered tree wire. This is something you would use if you wanted to put something overhead and you wanted to protect the wire against tree contact. And then an older type of a three-phase cable that you'll see is a cable that has paper. It's impregnated with chemical. It kind of looks like a waxy type of a substance. But basically this paper insulates the cables from each other. And this is what you'll see in older locations, especially like in downtown area cities. You see a lot of this older type of a cable. So important part of cable is the cable insulation. And so this is what separates the conductor from the neutral. This is what provides the, I guess, make sure that you're not shorting the cable and the conductor and the neutral together, right? And what's important about the insulation is when the cable heats up, you want to make sure that that insulation doesn't break down. These cables can get rather hot. And so you want to make sure you've got an insulation that can withstand the higher temperatures. Old days, we used to use like a paper insulation. Maybe this kind of goes back to the time of Edison. But now we're using different sort of plastics. And so you'll see terms like polyethylene or cross-linked polyethylene or ethylene propylene rubber. And so we'll have abbreviations for these like XLPE, right? That refers to the type of material that's used in the insulation. As far as characteristics of the insulation, that's what's most important to us is a dielectric constant. Basically, this gives us kind of like it says right here, a relative capacitance with respect to free space. And so if I have a dielectric constant that's greater than 1, what this means is this is going to have better insulation characteristics than, say, just like air, right? Which is what we had for overhead. But for cables, we'll actually have a dielectric strength, which is going to be maybe 2.3 times better than air. And so you're going to have volume resistivity. You're going to have a little bit of leakage in there. You've got losses as well. We're not going to concern ourselves with that. And so what we're going to be kind of focusing on in this case is we're going to be just kind of focused on using this dielectric constant because this is going to factor into the equation for capacitance. All right. So when we talk about cables, and like I said before, what we're going to be kind of focused on is we're going to be kind of focused on a concentric neutral type of construction. You again have the conductor in the middle. This is going to consist of multiple strands twisted together. And in order to protect the insulation, what we do is we put a very thin conductor shield around there. Then you have the insulation, all right? So this is basically what's going to separate the concentric neutral from the conductor. And then you're going to have an insulation shield. This is what's going to protect the insulation on the outside from the concentric neutral wires. And then you may or may not have a jacket. And a lot of times this is also a kind of a hard plastic material. You'll also see in some instances like an armor around it, like a metal armor to protect against digging. And so if this is buried and somebody's digging potentially around your cable, you might put like a steel conduit around it in order to protect it. This shows a cross section of a three-phase cable, and it shows that you basically have the three-phase conductors. This one doesn't show a separate neutral in this case, so you have to have a balanced load. You would have insulation around each of the conductors in here, and in order to keep the conductors sort of together, what you have in here is you have some fill material to kind of keep the conductors in place. And again, you would have a plastic jacket around here. So when we're talking about three-phase, we could either have a three-phase cable. That would probably be more convenient, like for industrial installations, or you can have like three concentric neutral cables, say like for phases A, B, and C, and then you could just kind of lay these in the ground, or you could put these in ductworks, whatever. And you could actually make it out of three single-phase conductors as well. So these conductors are typically copper or aluminum. The wire sizes are the same as the wire sizes we would use overhead. So we talk about 1/0 or 4/0, whatever, just like we do about overhead. And basically, again, you're going to have this kind of polymer plastic type of cover protecting the outside of the cable. So for underground construction, there's a couple different ways we can do this. We can put this in ducts, where basically, we can position the cable underground so the cables are far enough apart so we get proper cooling, or we can do direct burial in earth. And for the duct applications, basically what we're going to be doing when we put these underground is these are going to be kind of in a fixed sort of topology. And you'll see a lot of times, you see these manhole covers on the street or on the sidewalk, where those are the access points if you want to get into the ducting system and maybe pull a new cable or do some maintenance on an existing cable. You want to make sure in this case when you have these ducts that you don't have so much cable loss, I²R loss, that you're going to overheat the conductor. So that's a big consideration. Direct burial is when you just lay this underground, right? And so you basically dig a trench and put the cable down and fill the trench back up again. And in this case, what you have to make sure that this has a sheath or a jacket covering to protect against the corrosives in the soil. So you want to make sure that if it's acidic soil, it doesn't damage your cable. The other thing you have to kind of watch out for too is mechanical stress. And so this is going to have this cover on top of it, and you got to be really careful when you're laying the cable that you don't bend it, because actually can weaken it and can cause premature failure. So this shows a case of underground duct. Basically, this is a concrete sort of a form here, and you would have like a cable in each of these different positions here. Again, what you have to be concerned with is you have to be concerned about I²R losses. There's actually computer codes that'll actually help you compute what types of heating effects you would have, and whether if you have a certain amount of load or not, you're going to be causing too much heating. And then for underground, one way you could do this is you could actually just dig a trench and you can lay the cable down. They've also got special machines as well. And if you go up on YouTube, sometimes you can see some video of these trenching systems where basically they can put cable underground, actually without having to dig a big trench. They have different sort of ways they can, push cable underground without disturbing the topsoil too much. And as I mentioned before, when we're laying out residential systems, and what you're going to see is a lot of times these are going to be laid out in loops. So let's suppose we have like a single phase residential service we want to provide. What you would have is you'd have your primary backbone, and then you would tap into 2 points, and these are going to be fused taps. The cable will go down the side of the poles in a pipe. It'll go underground. And what we're going to do is, if we have these different transformer locations, what we're going to do is we're going to have an open point. This is the normally open connection here, such that if I had a cable fault, and let's suppose I had a cable fault, say like right here, well, I would disconnect here, I would disconnect here, I would close the switch, and what that enables me to do is to backfeed the load in the other direction. And so cable systems are typically set up in loops because if you have a cable failure, it takes longer to fix an overhead. It may not fail as often, but it takes longer to fix. And so you always have to have some sort of a backfeed path if you're going to be dealing with with a cable system. A lot of times, if you're a power engineer, you're going to be asked to look at the feasibility of doing it like an underground sort of construction versus just doing it overhead. And as far as just some comparison notes, if we were going to compare like underground cable to overhead, I would say just in general that cable systems can be more reliable. Obviously, they're not subject to trees falling into lines like overhead or animals getting into overhead. The fault rate for a cable is usually going to be less if the cable's not damaged or if the cable's not too old. The problem you're going to run into on the cables, though, if you have any kind of a fault, the faults are always going to be permanent. They're not temporary. And so later on, we talk about reclosers. You don't want to do reclosing actions involving cable faults. The other thing about cables is that if you bury these in ground, they typically can have some pretty good heat dissipation capabilities. And so if you're putting in ducts, you might have to worry about the heat dissipation in that case. But in a way, it's going to be more predictable in a way because it's always underground. It's not going to be overhead. The ambient temperature is always going to be about the same for cable systems. So that could actually be a little bit more predictable. The asset life for cables is going to be maybe 20 or 30 years. If we're talking about overhead systems can maybe be 50, 60, 70, maybe even like 100 years conceivably. And so this is the thing we have to deal with is if cables start to fail to some extent, we can cut out the bad sections and splice the good sections back together again and fix it. But when cables get too old or they get damaged, then they have to be replaced, which is going to be fairly expensive. And so that's the thing we got to kind of consider is the fact that since it's underground, it's harder to keep repaired. It's more expensive to replace and would have to be replaced more often than an overhead system. And so, this is where you kind of have to get into, the pros and cons and do some economic analysis if somebody's interested in like converting overhead to underground service. So as far as a cost comparison, this is something from an old reference. This is from 1991, so this is like 30 years old by now. But what I would say in here is look at the relative difference for these different sort of projects. So don't focus on the dollars per feet, but focus on these ratios right here. And in general, what you're going to see is if we're talking about like underground versus overhead, maybe there might be a factor of 2 or 3 difference in that a cable system might be 2 to 3 times more expensive than having an equivalent overhead system. And so you have some advantages in terms of aesthetics. It looks nicer, but you have to just always consider that these cable systems are going to cost more. And so anyway, here's some older numbers, and there might be some updates to these somewhere. I haven't seen it myself, but again, don't focus on this dollar per foot cost. Just focus on the ratios. And then this just summarizes some of the advantages and disadvantages I just mentioned here. So if you go to the vendor sites, the vendors of these cables will normally have tables that show how to calculate impedance. And they'll have these for different spacings. And what we mean by spacing is what's the spacing when this is buried underground between the cables. So if they have a 7.5 inch spacing, that means this is going to be buried in a trench or underground. And these adjacent cables are going to be 7.5 inches apart. And what the vendors of the cables will do is, depending on the cable type and the sizing, what they'll do is they'll tell you, what's the positive sequence impedance and what's going to be the zero sequence impedances. Now, what I'm going to show you in this lecture is how we do those calculations, but you could also get this from the vendors as well. You'll note that they have what we call a full neutral and a 1/3 neutral. And what the difference is that if you have a balanced 3-phase load, you shouldn't have that much current coming back to your neutral. And so if you want to save some money, you might want to use a smaller neutral wire. They call it third neutral. A full neutral would assume that you have a large imbalance where the neutral current could be the same magnitude as the phase current. And so you need a thicker neutral wire, and that's what a full neutral is. And so depending on the balance of the loads, you might have like one or the other. Right, so now what we want to do is we want to get to the cable impedance calculations, and I think what I'm going to do is stop here. And when we pick up on this again, then I'll kind of go through, given the physical characteristics, then how do we calculate the series resistance reactance and also the shunt capacitance.